Okay, in 3.11 we're going to talk about differentials. And differentials are basically tangent line approximations. Well, they're the approximate change based on what the tangent line would say. So let's look at the tangent line real quick. So if I have the point x, f of x, and f prime of x is the derivative at, let's say, x. Let's put x naughts on these things. All right. Then we can get the tangent line at x naught by taking the point slope formula, f of x minus f of x naught. Let's call this not f because it's not the actual function, it's the tangent line. So this is, we'll call it t for tangent line. T of x, the output of the line, minus, so this is like y minus y1, or y0, equals f prime at x naught, that's your slope, times x minus x naught, right? Okay, so this is the change in the tangent line. This is delta y in the tangent line. And I'm going to draw a picture to represent this, but this is delta x just in general, right? It's the change from x naught to x. And this is the slope of the tangent line. Okay, so let's draw a picture. Here's our curve. Let's take the tangent line here. Okay. So if this tangent line, this is the function t of x equals y, then this is at x naught, this is a point at x naught, f of x naught, right? And if I move a little bit to the right, maybe delta x, and I end up at x here, this would be at x comma t of x. The point on the actual function is going to be different, right? This is the point x comma f of x. But these two things, these are approximately equal by tangent line approximation stuff. Okay, let's zoom in on that. I'm going to draw in this triangle. Okay, so this triangle with the tangent line being the hypotenuse, this side's the delta x, this side's the delta y, right, of the white triangle. There is another blue triangle here that gives you the actual change in the function, right? So the actual change of f of x minus f of x naught, that's the actual change in the function, is approximated by t of x minus f of x naught, right? And so t of x is approximately f of x. And that's all that we're saying with the tangent line stuff. Okay, so if we could figure out how much t of x changes, based on just some multiplication in the slope, we could figure out approximately how much f changes. And that's what this differential stuff is. So the differential, zoom back out there. Okay. The differential is a function in two variables. So we call it dy. This comes from like the dy over dx bit. This is equal to f prime at x times dx. Okay. So if delta x is bigger, then I move farther out on the tangent line and my approximation's different, right? So this is one of the variables. and x is the other variable. Where are you approximating it, and how much are you moving from that centered position, right? So it's dy is really a function in two variables, x and dx. Okay, and dx looks like it's not just one variable. It's a multi-character variable, but that's what it is. It's a function in two variables. Okay. So let's do some problems with these. Let's say a find a story problem here. A cube is measured with an error. What just happened? There we go. A cube with the edge length x is measured with an error of at most 0.5%, which is 0.005, right? Okay. Times x. So our error, x, we're given a specific measurement, and then we know that x lies between x plus 0.005x and x minus 0.005x. So our error, we take a measurement, and then we know that we're at most 0.5% off, so the real measurement is somewhere in this bound, okay, which is 0.995x to 1.005x. That's another way to write that interval. Okay, and now we're asked what's the maximum corresponding percentage error in computing the cube's surface area and volume. Let's just do the volume for this one. Okay, so we've got this cube, and we know that the edge of the cube has been constructed so that we have at most 0.5% error, and we want to know, like, if we thought that the volume was going to be x cubed, because there might be error in the length of the side that we measured, the calculation that we do for volume is also going to be uncertain. How much uncertainty do we have in that volume? So let me kind of draw a picture, right? So here is a cube with a side length of x, let's say x, but our measurement might not be perfectly accurate to what the cube actually is. Maybe the cube extends a little bit this way, right? And then also a little bit higher. So I put like more stuff here on the cube, right? And then there's stuff on the back side too, right? So that if the measurement was a little bit off, maybe I've got 0.5% farther this way, 0.5% farther this way, and 0.5% farther that way. I'm going to get a much bigger volume, right? Because I have added stuff on 3 of those sides. Okay, so we know that dy is equal to, well, v, let's go dv. v is x cubed, so dv is equal to 3x squared dx, right? And dx is how much the x value can change in sort of absolute terms. So this is equal to 0.05 x. Sorry, 0.005 x, 0.5%. That's how much dx could be, right? That's how big dx could be. So if I put in 0.005 x, the amount that this volume could change, because this is the biggest amount that the side length could change, the amount that the volume can change would be 3x squared times 0.005x, which is 0.015x cubed. So I could have a 1.5% change in volume. Okay, so a 0.5% change in measuring the side length would give you an up to 1.5% change in measuring the volume, right? Which is a pretty big change. And this is just a linear approximation, but that's how these derivatives or differentials work here. If I wanted to find the absolute max, right, I have to sort of see in this cube what have I added on. Well, let's draw this a little bit more carefully. Okay, so I add stuff onto the top. And that's an x squared onto the top times this little value here, which I'm going to call dx, right? I get to add that onto the side as well. And so there's a second x squared dx on the side. Let's put this one on the front so that we can see it when we draw it. So on the front, I have another x squared dx. But there's some bits that I haven't drawn in that aren't part of this cube, right? I've got that bit that needs to be filled in. Got that bit that needs to be filled in. And I've got that bit that needs to be filled in, right? There's these long pieces that need to be filled in as well. And each one of those, that's x long times dx squared, right, on one of the square sides. So I need to put plus 3 of those. And then there's one last bit that hasn't been filled in yet. That's this cube right here. I haven't filled that in yet. And that would be a dx cubed, right? So the total error is going to be, it's going to be x squared times dx and 3 of those, plus I will have 3x dx squared, plus we'll have 1 dx cubed, right? That's how much total error I would have. And so if this is up to 0.005x, I can put that in to each of these spots, and in this first spot we get 0.015 x cubed, plus we get 3 times x times 0.005 x squared plus 0.005 cubed, and this should be a squared, x cubed. Okay. So the reason that the approximation that we had up here of 1.5 was so good is because these extra terms, that tiny little dx percentage change gets squared, it gets cubed. If you have higher powers of x, these things, they become sort of really, really small. 0.005 is already small, but when I square it, it becomes even smaller, or when I cube it, it's even smaller yet. So we kind of just ignore these terms with the tangent line approximation stuff. So that's kind of the idea behind these differentials. You're doing tangent lines approximations, and you're ignoring these higher order terms because small changes become tiny, tiny changes in these higher order terms. Like the more zeros you have here, like in the second order term, you double them. So if you had 3 zeros in a second order term, you actually have 6 in that full term, which makes it sort of really small, and we kind of ignore that as I get smaller and smaller tolerances on how things work together. Okay, in the next video I'm just going to do some problem solving stuff, but this was kind of the ideas in what the differentials are all about.